All right, guys, today we're going to be talking about the properties of various compounds. You guys, there's three major types of compounds or substances where we've learned about so far. Ionic compounds, remember a metal and a nonmetal from your periodic table. Covalent compounds, which are molecules formed from nonmetals, and then also metals. It says, I'm no fan of technology. Have you noticed how difficult it is to eat homework these days? See what he had to do? He had to eat a laptop. Okay. Don't do that when you guys start driving. Don't have paint buckets secured. She says, I got a nose job last summer. Well, you know what? I decided to do my lips and cheekbones. She says, this isn't even my real head. You guys are taking plastic surgery to ridiculous extremes. Be happy with the way God made you guys. Okay, so the first thing we want to look at are property of ionic compounds. So you guys write that down. That's when we have a metal with a nonmetal. Whenever you guys think of ionic compound, just think of salt. Salt's the easiest one to think about, NaCl. Okay, look at it. So this is a salt crystal.
Here, a small crystal of solid sodium chloride is shown. It is transparent and has 90-degree angles at the sides. When a knife blade is placed on it parallel to one side and tapped with a hammer, the crystal cleaves into two pieces, each with a very clean, plain edge. Now the piece that was cleaved off of the original piece is examined. The knife blade is placed on it at a 45-degree angle to a side and tapped with a hammer. The crystal shatters, but part of it cleaves parallel to a side.
So guys, this is a typical of ionic compounds. Once again, just think of salt. You see when force was applied to it, you see it broke. Now here it would explain why.
In this atomic scale view of sodium chloride, when the crystal is struck, ions with the same charge are moved near each other. Since like charges repel, the crystal cleaves into two pieces along the plane where it was struck.
You guys see why this is? Because ionic compounds, you guys, like if you had a salt crystal, it would look like this. It would be alternating sodium and chloride ions, right? You guys remember in an ionic compound, electrons are lost or are transferred from the metal to the nonmetal. So the metal becomes a positive ion and the nonmetal becomes a negative ion. So what's holding these together is the attraction between the positive and negative ions. So this would be like a salt crystal, sodium and alternating chloride ions. Look kind of something like this. And you guys think about it, these are held together very tightly, right? Because there's a strong attraction between these oppositely charged ions. Now, if you apply a force, you guys see it's a very organized framework. Notice each positive ion is surrounded by negative ions and each negative ion is surrounded by positive ions. If you apply a force, you see what's happening. You're disrupting that organized framework. So now, if I push down here, like this is like the knife blade, won't I bring a positive ion now in close proximity to another positive ion? And what do we know about like charges? They repel. That explains why ionic compounds like salt, when you apply a force to it, will break. Because this is kind of interesting. This is showing how we could form salt. Because this is chlorine gas.
A small piece of sodium metal was placed in a flask containing yellow chlorine.
And normally
gas.
I would do this in class for you guys. So we have some
The
pure
flask
sodium.
also contains sand to prevent the heat which will be generated by the reaction from cracking the glass.
And that's just sand at the bottom. That's just to absorb some of the heat. So we have sodium, pure sodium, which once again is very reactive.
Initially, no reaction is observed.
And we have
between
chlorine
the
gas,
sodium
that
and the
yellow
chlorine.
gas.
The reaction will be initiated by adding a drop of water to the sodium.
So sodium's so reactive, it'll actually react with water, generate a lot of heat, initiating the reaction between the sodium here and the chlorine gas, and now look what results. What you actually have here is a white film along the side. What do you guys think when you had sodium combining with chlorine? What do you guys think you end up producing? You end up producing salt. You could actually scrape that off, put it on your fries. I wouldn't advise you do that with the glassware. Okay.
Molten ionic compounds conduct electricity, but covalent compounds do not. Why is that?
Well, in our model for ionic compounds, like sodium chloride, ions are the main building block. In the liquid state, these charged particles can carry electricity.
So now you guys are talking about conducting electricity. So here I have this device. Here hopefully you guys can see it. I don't have a lot of room. Hopefully you guys can see it. Here it's a light bulb. And I don't know if you guys can see it. It's actually plugged into a light source. But the question is, why isn't it turned on? Somebody will say, well, you didn't put the on switch. It doesn't have an on and off switch. So there is electricity there. You guys will notice there's 2 electrodes. Hopefully you guys can see in the picture here. There's 2 electrodes. Some of you guys might know, if you've had some background on electricity, what else do you need besides a power source to power the light bulb, right? And you guys know electricity is just a flow of electrons. Well, electrons are coming here. Well, you need what's called a complete circuit. You guys can see how these are not touching. So if I wanted the light bulb to come on, I would actually have to provide something that's conductive. That means it allows electrons to travel from one electrode to the other, allowing for a complete circuit, allowing for the light bulb to turn on. So what could I use? You guys, what do you guys know that's electrically conductive? Think about, what are your wires? We have wires. What are they made out of? Obviously, they have a rubber coating, which is insulation, so we don't get shocked when we touch it. But the wire itself is made out of metal. So here, I'll just use this screwdriver here and check this out. So all I do is touch it. Now these things are a little rusted, so it takes a little. But you guys see, every time I touch it, now the electrons can travel from the positive electrode, the negative electrode, through to the positive electrode, completing the circuit. Electrons are able to travel, and that energy is used to power the light bulb. So here's the question. Okay, so let's say I had some salt. Okay, I have some salt here. Okay, question is salt itself electrically conductive? You guys watched that video right there. Let's see. So I'm hoping you guys make predictions when we do this, before you actually see it. So I'm going to put this in here, and we're going to see, is salt electrically conductive? And I'm putting it in the salt, and is it turning on? No. So what does that tell us? Are electrons able to freely travel through the salt from one electrode to the other? They are not. So salt itself is not electrically conductive. Now you guys looked at this, and it seems like I'm kind of contradicting, but now kind of see the difference, okay? Look at this.
When wires connected to a light bulb and battery are placed into a sample of salt that has been melted by heating with a burner, the light bulb lights, showing that molten salt conducts electricity.
That's lighting. But you guys, what was the difference with that compared to what we just observed there? There, it was solid salt, right? Here, what did we do? They called it molten salt. What did we do to the salt? You heated it up. And essentially, what's going to be the difference? The difference is, in both cases, in an ionic compound, we have ions, right? But in the molten, in the liquid phase, those ions are now free to move around. Look at how it works. Okay, so here's our light bulb. Here are our 2 electrodes.
Here is what happens when the wires connected to the light bulb and battery are placed into molten salt. There are many ions, and they allow charge to be transferred through the liquid salt by moving toward one or the other electrode. This completes the electrical circuit, and the light bulb lights brightly.
So ionic salts in their molten state are conductive. You guys see what's happening? You see how you have to have a flow of electrons, and that's what powers the light bulb. If the electrons can't travel from one electrode to the other, from one lead to the other, then you're not going to have a flow of electrons, you're not going to have it lit. So in this case, because it's in the molten state, those ions, you guys see in the solid state, these ions, they're not free to move. They're just locked into place. You guys remember how rigid they are. But when we heat it up, the ions are now able to freely move. And so what happens is now, when the electrons come here, right, they're going to attract the electrons are negative, they're going to attract the positive ions. The positive ions are going to accept the electrons, and now they're going to continue to freely move to the next electrode and thus give up the electrons. So they serve as a transporter of the electrons from one electrode to the other. But that's only in the molten state. Okay, guys, we want you to write some things down here. Okay, properties of ionic substances. Here's one property, guys. They have relatively high boiling and melting points. What we're saying here is, if we want to melt the salt, you're going to have to input a lot of energy. Why is that, guys? Because of the extra strong attraction between the positive and negative ions. There's a strong attraction, therefore it's going to require a lot of energy to get those ions to separate. You guys see, solids are brittle. You guys think about it. So here's a piece of salt. and then that's kind of a large piece, we call it rock salt. Same thing that we've seen here, okay? So you guys, let's say I apply a force to it. So here I have some pliers. Now what do you guys think is gonna happen when I push on those pliers? What do you guys think? And you guys, I didn't use any superhuman strength. Salt is very brittle. You guys remember why? Because what you're doing is disrupting that organized framework of the alternating positive and negative ions. Next, they do not reflect light. You guys, salt is, right? It's not shiny, okay? And notice this, guys, ionic solids do not conduct electric current. So we're kind of just summarizing what we'd already looked at. And you guys remember why we were saying that? Because even though the solid salt has ions, the ions have to be able to move in order to conduct and transfer electrons through the substance. And then you guys could probably guess ionic solids don't, but you guys don't bother with that. You don't have to write that. When molten, they do conduct electric current. So in their liquid state, they conduct electric current. You guys, everything we've been talking about so far is ionic compounds. Remember, a metal and a non-metal. That's when you're going to create these ions as electrons transfer from the metal to the non-metal. Okay, we're going to move on. The next one is covalent compounds. For that, she says, they're watching a movie. I love how you watch romantic movies with me, you know. I think a guy who isn't afraid to show his emotions is super hot. I guess I'm just a big softie. So you guys, covalent compounds. Here are some common covalent compounds. Notice that, guys, NH3, that's ammonia. That's your active ingredient in Windex, for example. CH4, that's methane. That's the gas that we use in the Bunsen burners when you guys return to school. Oil or gas as our hydrocarbons, a lot of hydrogen and carbons. Carbon dioxide, what we're breathing out with our hot, funky breath, and then we know water. You guys, look at all those compounds that you see there. What do you guys notice about all the atoms? Nitrogens, carbons, hydrogens, oxygens. Where are they on the periodic table? Guys, they're all on the right side. They're all what? They're all non-metals. So covalent compounds are those compounds that form as a result of combination of non-metals. Okay? So here's some properties, guys. Notice they have low melting points and boiling points. So that means that the molecules of covalent compounds aren't held together as strongly as the ions in an ionic compound. Therefore, you only have to heat them up very minimally. In fact, you guys, a good example here. Sorry, guys. Still here, guys. So a good example of a covalent compound would be like sugar. You guys, here's the formula for sugar. C12H22O11. That's your sucrose. Notice, look, it's got carbons, hydrogen, and oxygen. You're like, oh, that's probably a covalent compound. And you guys know, if you apply heat to salt at home, you guys won't be able to melt it. I tell you, you can try it, put it on your stove, obviously on the pot or whatever. You try to heat, you're not gonna be able to heat it. Your stove's not gonna get hot enough to melt it. But you guys, could you melt sugar if you heat it? You guys know you can. You guys know it turns, well, we'll see. Okay. Solids are soft and waxy. They're poor reflectors of light. So, okay, so that was kind of similar to ionic compounds as well. So here, you guys see, we've got some sugar, and look, you can melt it.
When wires connected to a light bulb and battery are placed into sugar melted on a hot plate, the bulb does not light. Molten sugar does not conduct electricity.
You guys see how that's different than an ionic compound? Here, it was molten. You guys know you can heat up sugar, and you guys see how it turns kind of, dark brown or even black eventually. And then when we put the light device in, it did not light up. It is not conductive. And you know why? Because in order to conduct electricity, what do you need? What did the ionic compounds have that the covalent compounds didn't? Are these ions, positive and negative ions, because you guys remember, electrons are transferred from the metals to the non-metals, creating these ions in a Covalent compound, you guys remember what covalent means? All the atoms, they're not transferring electrons between each other, they are sharing electrons. So you don't have these positive negative ions, and thus you're not going to conduct electricity. So they do not conduct electricity. Okay, guys, let's we're going to move on to our last type of substance, and those are metals. So you guys, if you would write properties of metallic solids, and I'm hoping you guys would already know of some different properties of metals. So you guys are hopefully thinking, just think of metals like here. I got a piece of metal here. It's aluminum. First of all, you guys, let me see what I got here first. Yes, you guys, first of all, look at it. What would you guys say about metals? They're what? Aren't they shiny? Metals are shiny. We say they have luster or reflectivity. That's just a fancy word for shiny. You guys, metals are shiny. Another property. Oh, you guys, what do you guys predict? Let's say you guys remember I did this with the salt. You remember it just crushed. Let's say I take a piece of metal and I do the same thing here. And I would normally do this with a hammer if you're here, but I don't have anything to do with a hammer, so I'm just using some pliers. What do you guys think? Even with Mr. Willison's superhuman strength, you guys expect it to just crumble and be brittle like it was with the salt? Let's see. I don't know if you guys can see. I did move it a little bit. I don't know if you guys can see. It was like a perfect circle. Now it's kind of flattened. So, you guys, in that case, it didn't just crumble. And what we would say is metals are malleable. The word is malleable. So when you apply a force to it, you can alter the shape of it, but it's not going to crumble or fall apart like a brittle substance like an ionic compound. We'd say it's workable. Ductile means you can stretch it into a wire. So there's a certain way of how the atoms align themselves that cause these certain properties. So we're going to look at that here in a little bit. Another thing, you guys skip number 3. We won't do number 3. Number 4, they are good conductors of electric current. You guys remember we already knew that. I didn't even have to demonstrate that for you. You guys know our wires are made of metal, and so you guys can see it does allow electric current to travel through it. And then last thing, they're also good conductors of heat. You guys, and that would explain why we use metal pots and pans, right, on our stove, because we want to transfer the heat from the burning gas directly to our food, and so we're going to use metal to do that, because then heat transfers relatively easily. So here's the reason why, guys. What might explain all of these properties that we saw, why they're shiny, why they're malleable, why they're good conductors of electricity. And here it is, guys. Maybe you guys, what this is showing is, so just imagine in a piece of metal, okay? Just imagine trillions and trillions of metal atoms. Well, the metal atoms, you guys got to remember, the metals, they're on the left side of the periodic table. Remember, they have loose valence electrons. So this is what this is showing here. That's not a nucleus. That's showing the atom, the metal atom, with all the core electrons, and then these are just representing the valence electrons. And what you'll notice when you guys look at this picture here, you guys notice, does it look like the metal atoms are nice and ordered in a nice ordered framework like the ionic compound? Hopefully you guys notice, no, they look a little bit more disordered. And that would explain why when you apply a force, with like the pliers or a hammer to a metal, you can disrupt it and it's not going to shatter. You guys remember the ionic compound will break apart because you're now misaligning the alternating positive and negative ions. But here, you apply a force, you can just, it's malleable, it is not brittle. And that's because of it's not in an ordered lattice structure like your ionic compound. And then, you guys, metals also have these loose valence electrons. That explains why they are shiny, because that's what's happening when energy hits it. Electrons get excited, they can jump to higher energy levels, and as they fall back down, they give off light. That explains in part why metals are shiny. And then why are they good conductors of electricity? You think about it, guys. These electrons, they're pretty delocalized. They're not really, like the valence electrons aren't localized just to that particular atom, but they're kind of free to move between different metal atoms. Thus, the easy movement of those electrons makes for the high conductivity, electrical conductivity of metals. Okay, guys, so hopefully you guys were able to pick up on some of the differences between ionic compounds, covalent compounds, and then the last type of substance we looked at were metals. All right, guys, till next time. Bye.